First off, the quiz. You're going to see lots of big capital letters, big angry looking letters. Oh. I'm not angry. And as you'll see, you guys both did very well, but you're going to see that it's going to look like I'm yelling at you, and I am. For a couple reasons, okay? So, first off, I've hinted at this. I've tried to be gentle. Every time I see this in one of your homeworks, I make a note. And you guys just don't listen. So I screamed it on there. Stop using the quotient rule when it's unnecessary. Now, if you have something like this, please, by all means, use the quotient rule. Your life will probably be easier if you use the quotient rule. Yes, the quotient rule. But when you have something like, say, this, don't use a quotient rule. This is the same thing as this. And so if you need to take the derivative, right, like if it's easy, if whatever's in your denominator can just be brought up into the numerator by writing it as a negative power, then this will make your life a lot easier because it's this. Yeah. You know, and it's like, and it up until this point, it seems like it's not that big of a deal. Like if you're more, and I think I may have said, if you're more comfortable using the quotient rule, like I understand that, don't be comfortable with it anymore. Stop using it unless you absolutely have to. Let me show you, and here's one of the reasons why. Check this out. So, here's only one reason why, okay? Here's this. Let's say we're trying to take a bunch of derivatives for whatever reason. Watch what happens when you do this. X to the minus 1/2, right? Mm-hmm. Now let's take the next derivative. Now, here's another thing. This is the other thing I wanted to talk about. And I don't think I said this well enough. But whenever you're trying to find a pattern in something, like for instance, let's say we're trying to find the Taylor series of something. And so we want a pattern so that we could have some kind of formula involving n or whatever. In order to get that, we need to find a pattern. If you're trying to find a pattern in something, it makes your life a lot easier if you don't multiply this stuff out. And let's just see why, right? It's so hard to find the pattern if what you've done is multiplied the stuff out. But now, can you start to see the pattern here? Let's take the fourth derivative, right? We're going to keep this out. Here's this minus 3/2 minus 5/2. X to the minus 5/7. Yes. Yeah. Take the next derivative. F to the fifth. The fifth derivative is going to be 1/2 minus 1/2 minus 3/2 minus 5/2 minus 7/2 x to the minus 9/2. You can see the pattern much more easily. Whereas if you had multiplied all this out, you'd have negative 1/4 as that. Here you'd have positive 3/8. Then you'd have negative, that's going to be 16 in the denominator, and 15. Not easy to see the pattern there, right? And then what's 7 times 15?
It's like 105.
7 times 15 is 5. Wait, carry a 3, 3, 7, and yeah, there you go, 105. 105 over 32. Like, what the heck is that pattern, right? But if you don't multiply it out, you see the pattern easily, right? And I could bet that the next, like I'm not even going to look at this part and say, well, my bet is that the next thing's going to be a negative 9/2. And then the next thing would be a negative 11/2. And then so on and so on. And that's what I was talking about, odd things. And you wrote like, I don't know what you're talking about, odd stuff. But this is, so there's a couple things going on here. This is one reason why the quotient rule sucks for this. Yeah. There's one reason. And so this is just one reason why. Next week, if you're stuck on the quotient rule, you're done. You will not be able to advance. get in the habit of, because it's like, so like this. Well, I'll do it when we get there. I'll do it when we get there. But, so in other words, now this is not just for Taylor series stuff. Anytime you're looking for a pattern, don't multiply things out, because you just won't see the pattern, right? And so that's all I wanted to say about that. Otherwise,
I think I still find it just took a long time.
Right. And so, right, so, but the whole thing about the quotient rule is like what we're about to go into. If the only way you've seen these things before is the quotient rule. So like for instance, let's say we're taking a derivative of this right here. You could use the quotient rule if you wanted to, and your life's going to be really hard. Or you could say, wait a second, this is the same thing as x to the 5/2, which is the same thing as this. Can you take the derivative of that? Way easier. Done. Now try to use a quotient rule on that. You have, yeah, you're gonna have, it's not gonna look that nice. In fact, let's just do it just to really be, okay, this is gonna be over this squared.
So it's like 0.
X to the 5th. So 0 minus, leave the 1 alone, and now we have to do a chain rule here. So 1/2 x to the 5th times minus 1/2 times the derivative, which is 5x to the 4th. Now you have this, and this is another one of those reasons why you have a hard time seeing the patterns, right? So this is x to the 5th minus 1/2 x to the 4th. Now, good luck. Good, and then you're gonna have to do. Then you got to take a second derivative. And you're gonna spend forever trying to get this down to this right there. It's almost, if you can turn your function into something raised to a power, positive or negative, your life will be easier.
Yeah.
So stop using the quotient rule. It's been a suggestion up to this point. Now I'm telling you explicitly, stop it. No. Bad. Homework 23, page 310, section 5.2. Numbers 3, 17 through 29, odd. 33 through 39, odd. 43, 45, 51. Okay. Here we go. Let f of x equal x squared minus 1. Something like that. Now, use 4 rectangles to estimate area. I'm just going to say the area from -2 to 2 using midpoints. Okay, so we're going from -2 up to 2. And so we want 4 things. I'm going to chop this into 4 pieces. 0 would make this, there's that, and there's that. I made this easy because I just want this to be easy. Now, if we think about the rule for this, right, the area we're looking for is going to be f of x1 times delta x plus f of x2 delta x plus f of x3 delta x plus f of x4 delta x. Everybody comfortable with that?
Yeah.
Okay. But the thing is, these things, they need to be midpoints. Okay? So instead of, this would, by the way we were doing this before, this would be my x0. This would be my x1. This would be my x2. This would be my x3. And this point would be my x4. Yeah? And so there are 2 different ways we could do this, right? We could get my first box here if we're using the right hand, which is what this is, right? I've written up the right hand rule for this, okay? Or the right hand estimate. We could do it with the left hand by doing the boxes up here. But here, we're supposed to find the midpoints. So what is the, so now we have, in other words, we have 4 little areas we're trying to find. A1, A2, these 4 rectangles, A3 and A4. And if the midpoint, if we're using a midpoint rule, what we want to do is our first box here, that's going to be area 1, we want it to be the midpoint right there. That's all that is. What is that point? negative, yeah, negative 3 halves, or however you want to do it. So, right there is what we want, and we want this box right there. So, give me a second. I'm going to go ahead and do that. So, in other words, what we're doing here is we're saying, okay, we want f of negative 3 halves. We plug that in, whatever that is, that's the height of the box. The width of the box is what? What's delta x in this case?
1.
Yes. And let me see, and let's just see how we would do that. We would take the last point minus the first point. So 2 minus negative 2. Divided into how many pieces?
4.
4 pieces. And so that's 2 minus it, that's 4 over 4. That happens to be 1 in this case. Nice. It's almost like I chose something that would give us easy calculations. So now what about just going off the definition here? What's this going to be? What's the midpoint between here and here?
Negative 1/2.
Negative 1/2. What happens? Okay, so hold up. So f of negative 1/2 times 1. Now what's the next one? The next midpoint. So, oh, I'm sorry. So here, this box is the thing we're looking for. It goes to here, comes back up like that. Goes to here, comes back up like that. Here's this one. This is, what is it? 1/2. We plug that in, we get something here, and it goes like this. And that's the box we're using. So we go to f of 1/2 times 1. Plus, the last one is where?
3 halves.
3 halves. We plug in 3 halves, we get this box right here. And that's the box we're using for area. F of 3 halves times 1. I'm going to cut to the chase. You plug in a 3 halves here, and you get out a 1.25. The height is 1.25. I'll just do it. Negative 3 halves squared minus 1 is the function, right? Right, I plug in the negative 3 halves there. I get 9 quarters minus 8 quarters.
Wait, 4 quarters. 1 is 4 quarters, not 8 quarters.
Thank you! Gives us 5 quarters, which is 1.25. What happens here? We plug in a half. We square it. We get a quarter. That's a quarter minus 1 is negative 0.75. Okay, negative 0.75. Just going off the definition, that's what it tells me to do. We do the same thing here. We actually get the same output. You get a negative 0.75. Finally, you plug that in, you get the same thing as you got before, and it's 1.25, which is 1.25 and 1.25 is 2.5, minus 0.75, 0.75, that's 1.5, 1.5, interesting. It's okay, so it's just 1. Okay. What is going on here? Well, apparently we have something like negative area.
Yeah. Isn't there like infinite area under this?
Well, and that's the thing. And so we've been calling it the area under the curve, meaning between the curve and the x-axis. But we're going to extend this now. We're just going to say the area from the curve to the x-axis. That's the area we care about now. That's what our definition, just by using the definition, that's what it leads us to.
Okay.
And now we have something like negative area, and this shouldn't bother you because we've seen something like this before. Can there be a negative distance?
Yeah, there can be.
There can be, and it's not like a physical thing that you could look at, although it kind of is, because if let's say we're orienting our travel on a map, and we want to say if you're heading north, right, on the highway, then we'll call that positive distance. But if you're heading south, we'll just call it negative distance, right?
Yeah.
So it's kind of like, okay, from here, I traveled 50 miles north. So from 10 up to 60, I traveled 50 miles north. And then I traveled, let's say, 20 miles south, right? So my distance was a plus 50, and then I traveled an additional minus 20, Oops. Well, let's just pretend. Let's pretend he's here at 0. Started at 0. You went up 50. And then you went minus 20. Where did you end up? Your displacement, right, would be just that plus that. And it's like, yeah, okay, that makes sense. It's not like that the distance somehow is negative. It's just, it's assigned, signed. The distance has a sign to it. Negative just denotes that you're heading in a certain direction. Positive denotes you're heading in that direction. Same kind of thing here. Positive area denotes the area above the x-axis. And the negative area just denotes the area below the x-axis. And if you add them together, then that's like the, I guess it's just kind of like the total area that's above the x-axis. Is everybody comfortable with that?
What if you want to know how much area?
If you wanted to know how much total area there were, then what you do is that right there.
Oh, yeah. So
That way this bit bounces back up, and then you could plug that into your thing and you'd find it. But that's not as useful. It's actually way more useful to talk about the signed area. But that's what we're doing. That's what we're doing now. This is what we're doing. Okay? Okay, so you're gonna need to do a midpoint thing to do your homework. Everybody cool with midpoints?
Yeah. So
You just find the midpoint. And like, if it's something weird, right? If you've chopped your thing up into like a quarter, or let's just say, let's say it's really weird, like 0.7 and 0.1, 0.13 and stuff like that, and you need to find the midpoint. How do you find them?
Add them
And divide by 2. So if you have xi and xi plus 1, then this midpoint right here, we'll call it xi bar, is given by, well, you just add them together and divide by 2. You take the average. It's the average of the two. That's why we use a bar. Bar is often average, okay? And so right here, we would just say, okay, 0.1 plus 0.13 divided by 2. That's 0.23 divided by 2 is whatever it is. Who cares? I don't care. So it'd be 0.1 something. I don't know. But you get the idea, right? Mm-hmm. Okay, and you're only going to do that once, and pretty soon we're not going to be doing this at all anymore. That's why I'm just kind of blowing through this. Just want you guys to see some mechanics of visually what we're doing with all this stuff. Are we ready to move on?
Yeah.
Okay?
Yes.
Okay, so that's that stuff. Definition. Aha, here we go. Definition. Say you have, it doesn't have to be continuous. So, say you have a function, f, defined on a variable, defined on an interval a to b, okay? And say we've divided it into n intervals. Subintervals. So here we go, here's a visual, right? You have a to b here. And we're dividing it, we're going to call this x0. Here's x1, here's x2, and so on, all the way up to xi plus 1, all the way up to the last one, which is xn. Okay? Yeah. Okay. Those are the endpoints. And xi star is any x that's in one of these intervals. So xi star here would be any x that's in here, right? Between xi and xi plus 1. Okay. In that subinterval.
Including xi.
Absolutely. It could be xi or it could be xi plus 1. It's any one of them. Okay, that's the setup. You have that. Then the definite integral. The definite integral of f from a to b is is the limit of the sum. I goes from 1 up to n of f xi star delta x. And delta x is defined by b minus a over n. Okay? So there's nothing new here. Nothing new. This is just what we've done. This is what we did last time. And here we're just saying, like, it could be, in order to have this be a cogent definition, we want it to be as general as possible. And it turns out that no matter what x you pick in any one of those in any one of these subintervals, it's going to give you the same number when you compute this sum. Okay? Yeah. We're about to forget about this xi star stuff in just a second. In just a minute, we're going to say, well, since it doesn't matter, let's just choose one of the endpoints. That's what we're going to do. But the definition is that it's any one of these. Everybody okay with this? We're going to call this now the definite integral. And this is how we're going to write it. If the limit exists. If you take this limit and it blows up, well then the integral doesn't exist. Yeah. Okay? And we're about to forget about all this stuff. This is what we're going to be working with. Okay? Now a couple things about this. This is how you write it. This thing is called the integral sign. And it is, so check this out. Do you know what letter this is?
Greek.
It's a Greek letter what?
Capital epsilon?
Sigma. Sigma for sum. Do you know what this is?
No.
It's the Latin summa. Oh,
For some.
for sum! Only it's like the limit of the sum, right? So they're connected. They're connected. Okay, this is why it's not just we need this cool symbol. There's actually logic behind it. You're taking a sum. Well, let's use an S. What S? Greek, right? And it's a big thing, so it's a big letter. Right? I don't know. And okay, and so ditto here, right? Sum only when you take the limit of the sum, you get an integral. Now, a couple other just mechanical things here. This thing is called the lower limit. This thing is called the upper limit. Uh-huh. And they're just numbers, right? Just like so for instance, that thing that we did earlier, it was the function x squared minus 1. It went from -2 to 2.
Yeah.
And we have a dx here. What's that dx about? You've seen a dx before. Can you look at this and guess where that dx comes from?
The change in x.
Yeah, if you remember when we were dealing with, we had some function and we had some delta y, delta x, right? When we're setting up a limit, right? When we're trying to find the derivative, and we said that what you want to do is you find the change in y over the change in x. And I said that, and of course, yeah, it was as h goes to 0, and h was this bit right here. We said symbolically what we do is we could say that's dy dx, right? That is why that symbol is that. You've taken the limit as n goes to infinity. As you can see, n going to infinity makes delta x get really small. Same thing as when delta x was h itself, it gets really small, and we say we're going to call it dx. Same thing's happening here, right? The limit as n goes to infinity makes that thing infinitely small. It's right there. Right now, it's just a placeholder. And in fact, for years and years and years, you will not talk about that thing. It's just a placeholder right now. If you go on to do more advanced stuff, there are other ways of doing a definite integral. And then this thing could be different. You define this thing in a different way, then it becomes it. But pretty much standard is that this thing is the limit of that thing. Okay. And really, all it does, the only thing that we are going to use it for is just to tell us what the variable is. That dx right there means that when you see an x in your equation, so like we had, this is the thing that we were trying to figure out earlier. This just tells us that x is the thing, is the variable here.
Oh, wow.
So for instance, if you had a y and a z, this would tell you we care about x. Treat the others like constants. Okay? Or, you know, if I said, find a formula for ax squared plus b right here, and we want to go from -1 to 7, then we're talking about, okay, well, what's a general formula for this type of thing that has an ax plus b going from 1 to 7? So then the area that we're trying to find is this right here. That's what this thing represents, right? But it's like, well, what's the variable? Well, you need to tell me what the variable is. That's the variable right there. It's x. X is the thing. X is the input axis here. Okay? And so this also corresponds to what this is here. X goes from A up to B, right? So this is just notation, really. And that dx, it's called a differential, but right now it's the only thing we care about is it tells us what the variable of integration is. It tells us what the axis is named. Okay? Questions on this? It's just, now we've just given this thing a definition, and instead of having to write the limit of the sum every time, now we can just do that.
Yeah.
Nice. And this way didn't really tell us where we were integrating over, right?
Yeah.
It didn't tell, this you'd have to like go into it and see, well, xi is written like this.
Yeah.
So I guess we're going from 5 up to, if that's n, it would be n over n, so 5 plus 4 is 9. So you could say, oh, okay, so you're going from 5 to 9 of your function. Nice. Much easier, right? There's a lot of reasons why this is a superior way of writing it. Okay? All right, everybody good with this?
Yes.
Okay, now a few more things about this before we get into some stuff. So, another thing, well, I'll just say it. Here we go. This, whatever it is, from a to b, some a and some b, f of x, some function, is a number. It's a number, yeah? Right? Like, we've done this now a couple times, where we have something, right? Like last time, we had this function, f of x was x squared. We went from 0 to 1. And does anybody remember what that actual area was that we found?
3?
No, 1/3.
1/3. And so we could say then the integral from 0 to 1 of the function x squared dx is 1/3. It's just a number. Would it have been the same if instead of calling this the x-axis, I called it a t-axis and did this? Does that change anything?
No.
It's still the same thing, right? So in other words, it's just a number. We still would have gotten, if I would have changed this to t squared and did a dt, you'd look at that and say, well, the variable's t, so you're talking about the function t squared, yep, going from 0 to 1, same area. Nothing's changed. So, a to b, f of t dt. Would it have been different if I would have called it a z?
No.
No, if f of z dz, it's the same thing. Would it have been different if I had renamed this smiley face? Right? A to b, f of smiley, d smiley. It's all the same thing. And so, when you're looking at one of these, when you're looking at a definite integral, right, some number up to some number with some whatever, this is what we call a dummy variable.
Like, it doesn't matter.
It doesn't matter. You could put anything in there. And sometimes it'll be nice, like if you're working with, you have some function and it's involved with x and stuff like that, and you want to get something, it might be useful to say, you know what, my x involves something else. Let's just call it t. And we do it in terms of t so that you don't get things mixed up. Dummy variable, we've seen this before. That's what I called this a dummy index. Right? Because if you have some kind of, I don't know, I squared over n, something like that, It doesn't matter if it's I could have called it K.
Yeah.
Dummy index, right? It means the same thing. It means the same thing. Okay? Everybody cool with that? Okay? This thing. So just before we move on, I just said that this was the limit of a sum. Limit as n goes to infinity of a sum. I've been using I. Let's use K. K equals 0 up to n. 1 up to n. F x sub k star delta x. Okay? You see, I just changed. Oh, did I change anything? No, it's just a k now. It doesn't look like an I, it looks like a k. It's the same thing. Right? Okay? This thing is called a Riemann sum. Riemann sum. Named after, I think it's B-E-R-N. Did I write it down? B-E-R-N. Hard. Bernhard. Riemann.
Sounds German.
Very German. Although it might be Austrian. But yeah, right? Like Germanic, Teutonic. He's certainly Teutonic. This name shows up everywhere from here on out. This guy was super prolific. You could read about him. I suggest you read about him. So this is called a Riemann sum. There are other ways of getting this by coming up with something different. Okay? And there are other ways of just doing this just completely differently. Why might you want to do that? Here's a cool example. Let's let g of x equal the function 1 if x is irrational, if x is rational. Okay. That's a function. It's a perfectly good function. There's nothing wrong with it. You plug in one input, you get out one output.
We did this once.
We've seen this before. And so let's say we want to integrate from 0 up to 1 g of x with respect to x. What's the area under that function? Well, what does it look like? Well, it kind of looks like this.
Go with one.
It's just that there's no two dots on top of each other. What do you do? Well, it turns out Riemann sum cannot give you an answer for that. So for almost all the functions that you're ever going to care about, this works. There are exotic functions that people started working on, and they said, this doesn't work with that anymore. We need something different. And so there are other ways of figuring out what the area under that is.
Like, the area between the two, or like what is under?
Yeah. Well, if I just said what's the integral of 0, so in other words, how much
0.
how much area is between 0 and the x-axis? Well, it's 0. Yeah, right. And so, but now what is going on here? Is there a way of it? There is a way of doing it. It turns out to be 1. But not with a Riemann sum. You ain't gonna find that with a Riemann sum. And however, if we change this, so it's 0 if it's irrational, but it's 1 if it's rational, then it turns out to be 0. What?
Wait, but
What?
don't the lines keep going out?
Yeah, we're only going from 0 to 1.
Sorry.
Oh, because there's so many more irrational numbers.
Yeah. But again, this doesn't work here because it's like how can you define an area under a dot basically?
Yeah.
And one of the ways you could get to this right here is by, what was the first step? I even wrote it on the board. Step 1, when you're trying to figure out an area, what do?
Delta x.
Well, we
Split it out.
we partition the domain. We chop up the domain. Another way of doing this. So this is a Riemann sum, and your book doesn't call it this, but this is the Riemann integral. If you say that, everybody will know what you're talking about. There are other kinds of integrals. One of them, I think I spelled that right, Lebesgue French.
Yeah.
The Lebesgue integral says, instead of starting by chopping up the domain, let's chop up the range. We'll partition the range. And then do some magic stuff. And when you do that, then you can actually do this.
That sounds hard.
You won't see that unless you're a math major in your senior level classes. And it's the bane of everyone's existence. And so, anyway, so there's a reason why you might want to set this up differently, but for almost all the functions that you're ever going to care about, unless you're going into some weird math stuff, this is an integral. Okay? That's a definite integral. Okay. All right. I just had to say that for completeness. Question. 0 to pi over 2, to 2 pi of sine x dx. What do you think that might be? Let's look at it. There you go. Let's graph it. Okay, it does this. There's 2 pi. So we want the area. Okay, so we have, this is the area we're looking for. There. There's that area right there. Do you think those are the same size?
Yes.
Yes.
So what do you think this might be?
Oh, it's just a parabola
pi.
times 2.
There's no parabola. This is not a parabola.
Well, there's
So is this a positive area or a negative area?
positive.
It's a positive area.
Oh, right, I forgot.
Is
Oh, it's
this
just
a positive?
0.
Yeah, good, right? Because whatever that area is, it's negative. I'm telling you, it's the same thing as that. And so this guy turns out to be negative. Okay. Turns out to be 0 because however much that is, that's exactly the same amount, right? So the total area that you're looking for is A1 plus A2. Well, A2 happens to be negative A1. It's just the negative, it's the opposite sign, SIGN. And so when you add them together, you get a big fat 0 right there. This is a really nifty way of, like, if you could just use your brain for a minute and go, wait a minute. That's gonna do, yeah. And so, there you go. Okay. Okay, all right, now. Here we go. Theorem. Theorem. If f is continuous on an interval, a to b, or has finitely many jump discontinuities, remember, jump discontinuity is it's doing something like this, and then it jumps up to here.
But there can't be infinite.
Not infinitely many. And that's what we saw with that weird g function I did, where it was 1 if it's irrational. That doesn't work because that ain't finitely many. That's infinitely many, and that's just too much. We can't deal with that. But if it has finitely many jump discontinuities, then I didn't say what this means. I should have put this with the definition. F is integrable. Integrable on AB. And integrable means that the limit of the sum exists. And this kind of makes sense, right? Like if you have some interval a to b, and you have some function, if it's continuous, well then, okay, it has an area, right? If it's not continuous, it does something like that, right? It ain't continuous there, well then integral doesn't exist. That's not, you don't have a finite, you're gonna blow up when you try to compute this, right? Right? Or if it does something like this, that's fine. You'll just take the area. That's an area right there. That's an area right here, You go to compute it, that will exist. It will converge. That's what this theorem is saying, is that it will converge. You're not, this is not going to blow up.
Yeah.
Okay? We're not going to prove this. In order to prove this, you know, it's a proof. Trust me, bro. We're good. We're good. That's a bit beyond. I think that's a bit beyond us to be able to do that. It's just the way it is. Trust me.
It kind of makes sense.
It does make sense, right? And that's another thing that I've been saying, like, this is another, like a lot of this, like the thing about the if you take, here's your xi and your xi plus 1, you could take any point in here, x star I is what we've been calling it, and use that point for your evaluation of the function. Right, or for your evaluation of the area, and it'll give you the same thing as if you use this or this.
Yeah.
Right?
Yeah.
Because this is going to 0 as you take the limit, and so it doesn't matter which point you chose. As long as it's going to 0, it's going to effectively be the same thing. We could actually, we can't prove that. It's true, we don't have the tools for that, but it's so obvious. I don't think we really need a proof. And so, here's another theorem. If f is integrable on AB, that is, the limit exists, right? Then the integral from a to b of f of x dx is equal to the limit of the sum. I goes from 1 to n of f of xi delta x, where, you're like, that's the same thing you just wrote. Yeah, I didn't do the stupid star thing. That's what we're saying. If it's integrable, and I'm just restating what I did a second ago, you could choose any one of these in there. So let's just choose the one over here. Right?
Yeah.
Just to make life easy, right? And that's what we're going to do. And it's true. You could. This is just formalizing what I said, that you could choose any one, it's going to work. Therefore, let's just choose the easy one to make life easy. Where xi is equal to a plus I delta x, right?
Yeah.
Because you're going from A to B, A up to B, and remember how we did this? I said there's your x0. This is your x1, and so on and so forth, up to xi, and so on and so forth, up to xn.
Yeah.
And each one of these spaces is delta x, which I'm going to write right here, b minus a over n. Okay? And therefore, right, how do you get to that one? You add on one of these.
Yeah.
How do you get to x2? You add on, plug in a 2 of those, all the way up until you get to the last one.
Okay.
And then in the last case, xn, this tells me, will be a plus n times delta x, which is a plus n times b minus a over n, right? The n's cancel, you get a plus b minus a, ends up at b, like we hope, right?
Okay.
Everybody with me?
Yes.
Everybody believe it? If you believe it, okay. Okay, so we're not proving that. This is one of those things, like I just said, you know, obviously, anywhere in here, as it's going to there, it's going to give you the same thing as if you just chose that point. Yeah, that should be obvious. Okay. Okay, now we're going to do the hard thing that I really don't want to do. I don't want this to take too long. I'm probably going to skip some steps. What I want you to do is just, like, I'm going to get an answer here. And I want you tonight, or when you're working on this homework, just verify this. See if you could do this from scratch, like cover up your notes. Do this from scratch and make sure we get the same answer. Okay. So don't just like zone out and look for the end, because you're going to want to see this. Okay, so ready? Here we go. Evaluate the integral from -2 to 2 of x squared minus 1 dx. Notice this is what we did earlier. This is the same function we started off with. It was this function right here. We went from -2 to 2, and we did it using 4 blocks to approximate it. Now what we want is the actual area. This is what we want right there. The actual signed area. Okay? So, in order to do this, we're going to need to put it into this form. Limit, and I'm not going to write the subscripts. From 1 to n of f of my xi's delta x, where delta x equals what? By definition.
A plus B.
No.
B plus
B minus A.
Minus A.
Yeah, how do you find out how long this is? You take that minus that, right? So this is 2 minus -2. So 2 minus -2 over what? N. Okay, so that's 4 over n. Now what's my xi? We start
-2.
Okay, -2
plus I times 4 over n.
I times 4 over n. Or I'm going to rewrite that as -2 plus 4i over n. Everybody with me on that?
Yeah.
Just to make my life a little bit easier. Okay, all right, so then f of xi is equal to what?
It's
-2.
oh
-2
I 4 over
4i over n
squared
squared minus 1. There's my function, okay? So now let's just plug these into here. And we get, okay, so it's the limit of the sum, I'm not going to bother with that yet, of this times delta x. Because remember, these are my heights. Don't mess this up and just multiply it by one thing, right? So there's this bit. There's my -2 plus 4i over n squared minus 1. There's that bit. Now I have to multiply that height by the width, which is 4 over n. Now, one thing to notice is this is just a constant times something with I in it. Remember our rules for this. If you have like a an, I'll use I so that we're not messed up here. I going from somewhere to somewhere, right? And you have some constant times that each time. Well, what you have, right, you have constant A1 plus constant A2 and so on and so on. You could just pull out the constant. A1, A2, da 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 da. So that's a constant times the sum of the AIs. Yeah?
and
See why I wanted to do this last? Because imagine trying to learn all of this right now.
Yeah.
That would be a huge pain, so I wanted to do that before. So I'm just going to pull out the 4n and deal with him later. Okay? And yeah, there's the limit.
Can you pull it out the whole limit? Wait. Yeah, you could.
Yeah. Hold up. But remember, no, because the limit is as
as
n
n
goes to infinity.
Yeah.
And this is in terms of I. This is one of the reasons I shouldn't have. I want to be lazy here. But as long as this doesn't have an I in it, you can pull it out. But now let's expand this guy here. So let's square him out. And we get what?
4 plus -8i.
Yeah, okay, so -8i over n. And then the inner would give you another -8i over n.
Plus 16.
So
squared.
how about minus
16i.
16i over n? And now what?
16i squared over n
Plus
squared.
16i squared.
Plus 16i squared over n squared. All of that, again, minus 1. Yeah? Okay, I'm going to get rid of this stuff here because we already got that. Okay, so this is the limit. 4 over n times the sum. Now let's clean this up a little bit. 4 minus 1 is 3. This is minus 16i over n plus 16i squared over n squared. Now, this is a sum. So we can break this up.
Yeah.
right? Because, right, the sum of AI plus BI is the same thing as the sum of the AIs plus the sum of the BIs,
Yeah.
right? So let's use that to our advantage here, okay? And we're going to say, okay, so this is the same thing as the limit, 4 over n. Now, the brackets might help. So the sum of 3, so it's just 3 plus 3 plus 3 plus 3 as I goes from 1 to n. Minus, I'm going to write that as minus the sum.
Of 3, that's just
I goes from 1 to n of 16I over n. Plus the sum as I goes from 1 to n of 16I squared over n squared. Right there. Everybody buy that? Did I do that right?
Yeah.
Now let's pull out some constants.
So you can pull out all the 16 of n.
Yeah, so okay, 4 over n. Now, so let's just do this one. This is 3 plus 3 plus 3 plus 3 n times.
Yeah.
That's the same thing as 3 times n. Okay, 3n. Minus, now, what can we pull out of here?
16 over
The n and 16.
There you go, because this is just 16 times 1 over n plus 16 times 2 over n plus that 16 over n can be pulled out completely, right? And you get 1 plus 2 plus blah 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 blah, right? So this is the same thing as minus 16 over n times the sum as I goes from 1 to n of just plain old I. Plus, what can I pull out of that one?
16 over n squared.
N squared times the sum as I goes from 1 to n of what?
I squared.
I squared. Now, I've been saying this for years and years and years.
Wait, can we factor this?
Well, we just kind of defactor. Well,
If
no.
we treat the sum as
Well,
there.
It doesn't work that way.
Oh.
It's not going to work that way. It certainly doesn't work that way. So,
Oh.
I just want to warn you, as you're doing this, you'll certainly want to use parentheses and brackets. They're going to be your best friends here. Because this is, as you can see, is going to take a long time to do these kinds of calculations, and your time would be much better spent just being very meticulous about using brackets and parentheses and getting it right the first time, rather than going, oh no, what did I do wrong? This isn't working out somewhere. So, okay, so now here we go on page. Page was it 303? You get this, the formula for this, you get the formula for this, and the formula for I cubed as well.
Okay, so then you just plug it in.
And so we're just going to plug it in. We're going to replace it, okay? And limit, you've done them before. We've proved them in class or in your homework before, last year. And so, I'm not even going to tell you.
We did do that.
The form, yeah, we did. Yes, we did. And so, it's as though I knew where we were going, and I knew that it would be a good idea to do this before getting into calculus. I wonder how I had that intuition. This turns out to be n times n plus 1 over 2. This works out to be n plus 1, and then
times n plus 2? All over 6.
it's n plus 1, and then 2n plus 1 over 6. Yeah. And then end bracket. Okay, now this is the part where I'm just going to jump to the chase, because I believe that you can multiply all this stuff out. Okay, you just keep multiplying stuff out until you get to... We'll do it here. And that's what I'll pick up. 4n. This works out to minus 5n minus 8 plus 16 thirds times n plus 8 plus 8 over 3n.
Oh yeah, because 16's
A bunch of stuff is going to happen here. And there's no wrong way to do well, there's a wrong way to do it. But like, like, if you just keep plugging along, like, you'll get to, it may look different, but you'll get to the final bit, as long as you've done everything right, to get that this is equal to the limit, as n goes to infinity, of negative 20 plus 64 thirds plus 32 over 3n squared. What happens as n goes to infinity?
It'll just go away, the 32 over.
This goes to 0. And so we get minus 20 plus 64 thirds, which is negative 60 thirds plus 64 thirds, which is,
120.
how about 4 thirds? Minus.
Oh.
Minus, yeah. Yeah, careful with that. Trust me, I've done, I know, okay? Like, that's gonna happen about 100 times. Just be careful. Be very, very careful, and then yes, that's your answer. I suggest that you do this from scratch. Like, if I just, as you're looking through your notes, go evaluate that, and then don't look at any of this right here, and try on your own to get all the way to here. And if you do, good job. Good job. Okay, here we go. Let's see how we're doing on time. Oh boy, we gotta hurry. Okay, there's still more to do. Still more to do. The derivative is a linear operator. Anybody remember what that means?
To do with lines.
Kinda.
Oh.
Kinda.
Oh, when you... Wait, I got that one.
If you take the derivative of a function that looks like this, right?
Yeah.
Then it's the same thing as a times the derivative of f.
Oh, yeah.
Plus b times the derivative of g. And this is how we were able to take really complicated stuff, right? Like 2x cubed minus 5x plus 3.
Yeah.
And say, oh, well, because it has this property, we could just say that's the same thing as 2 times the derivative of x cubed minus 5 times the derivative of x, well, plus 0, right? That's why we were able to do that, because the derivative has this property, right? And we could, and it's kind of nice to state it this way, as opposed to saying all the other things that you'd have to say, which is like that the derivative of a times f of x is a times the derivative. This like is, it just encapsulates it really nice.
Yeah.
Also from this we get the fact that because this is true, then the derivative of f minus g is the derivative of f minus the derivative
Because just plus
of g, because it's a plus and negative, and so it's just like saying the a is 1, the b is a negative 1, so that's just a 1, b is a negative 1, so it's the derivative minus the derivative. Right?
Yes.
Okay? Okay, here we go. The integral is a linear operator.
Oh, okay, so it just...
So just like
So a times the integral of f of x dx plus b times the integral of g of x dx. That's nice. Proof. We're actually going to do this one. The integral, so the integral here, this is equal to the limit of the sum of a times f of xi's plus b times g of my xi's, right? It's like, that's some function h right there. That right there is some function h, yeah?
Yeah.
Like that's h. The same way I could say like 2x squared plus 3x, that's my h. That's one function. How do you find the height of it? Well, you plug in some number into it. That's what it looks like when you plug a number into it, right?
Yeah.
Right? Right? Okay, so it's that times delta x. Right? That's the height, that's the width.
Yes.
Everybody with me on that?
Yeah.
Okay, so this is just a sum split it up, right? This is just a f of xi delta x plus b g of xi delta x, right?
Plus the
Plus the
sum
sum
of
of that.
Yeah.
Yeah, the sum of all, well, I haven't split it up yet. Yeah, that's the sum of each one of those, because I just multiplied him in.
Okay.
And now let's cut to the chase and say, well, that's the sum and that's the sum right there.
Yeah.
And since a is the same thing in every one of these, you have a times f of x1 times delta x plus a times f of x2, blah, 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 and so on and so forth. We could just pull him out. So there's the limit a sum f xi delta x. Same thing with b times the sum g xi delta x. And it's the limit of those. Well, it's the limit. So that's easy. This is just then the limit of a times the sum of f plus the limit of b times the sum of the g's. But that b is the same, right? And that's another one of the limit laws, right? Limit c times g of x
C times limit.
is just c times whatever the limit is, because that doesn't change as x changes. B doesn't change as n changes, right? This is the limit as n goes to infinity. B is just a constant. Same thing over here. A is just a constant with respect to that. So that's a times the limit as n goes to infinity of my this, which is my i's going from 1 to n of my f of xi's delta x plus the limit as n goes to infinity of the sum. Sorry, my b times that limit as my I goes from 1 to n of my g of my xi's delta x, which is
Just
a times, by definition, just by definition, it's the integral of my f dx plus b times the integral of g dx. So it all comes from the fact, like these are just this is just a property of sums. This is just a sum. You just happen to take a limit of it, right? And thanks to our limit laws and our rules of working with sums, it all just follows from what you do with sums. So that's cool. The integral is a linear operator. And because that's true, we could say, you know, I could write this down in a bunch of different ways. I could, like I did a second ago, say, well then some constant times a function is the same thing as the constant times the integral, etc. We can do the same thing with subtraction, right? F minus g dx is the same thing as, well, if the a is a 1 and the b is a -1, then it's f minus g. Yeah? Right? Obviously I've been dropping the region of integration, right?
Yeah.
Because the same way I do with the sums, when I'm going to write a ton of these down, I get lazy, and I'm just being lazy. That's all I'm doing. Okay? Everybody got that?
Yes.
Okay. So, here we go. From 0 to 1. 3x minus 1 dx. We could evaluate. Now, what you could do, since this is actually quite easy, you go down here to -1 and you do this thing. We could say, well, from 0 up to 1, we could find the area here, subtract them off, take this one and subtract that one, right?
Mm-hmm.
Right? Or it might be easier to use the fact that this is the same thing as 0 to 1, 3x dx minus the integral from 0 to 1 of 1 dx. And this actually might be easier too, to just do this, 0 to 1 x dx minus the integral of 0 to 1 of 1 dx. This is just the function 1 from 0 to 1. What's the area?
1.
1, right? Because it's a height of 1, a width of 1, so that's just 1.
Yeah.
Right? So that's minus a big fat 1. Now, 3 times, this is just the function x, and it goes from 0 to 1. So what's the area under here?
1/2.
should be 1/2, right? Because it should be 1/2 the base, which is 1, times the height, which is 1. So it should be 1/2. So that's 3 times 1/2 right there.
Yeah, so then it's 1/2. Just the whole thing.
So yeah, 3/2 minus 2/2 is 1/2. There you go.
Okay.
Life is easy. Oh, I did it, that's why. I did it from 0 to 2. And I got something different. Okay, all right. Couple more things, just you need to know. Okay, everybody good with that?
Yes.
Right? You could, so in other words, same thing like derivatives. Instead of plugging this into a difference quotient and stuff like that, it's like, well, I know what the derivative of x is, right? Or rather, it's easier to compute. In this case, you'd say like, well, it's easier to compute this than it is to try to find all of those areas and stuff. You could do the same thing. You break it down so that it becomes much easier to deal with, okay? And it's a linear operator. So you pull out constants. If it's separated by plus or minus, you just separate it out. Okay. So in general, from a to b, if you have some constant, a constant function, dx, well, let's think about that. You're going from a up to b, and you just have some constant function, whatever it happens to be, c. What's the area?
B times C. Wait,
A,
sorry.
A
A minus A
times
A minus a.
B minus A.
What?
B minus a, right? So this width is b minus a, right there. The height is what?
C.
So the area is equal to what?
B minus A times C.
There you go. C times b minus a. Nifty, right?
Yeah.
We did that with 1 a minute ago.
Yeah.
The constant was 1, all right? Now we also have, so that we did the minus f minus g is the same thing as the integral of f minus the integral of g. This one is going to come as a surprise. The integral from a to c, f of x, plus the integral from c to b of f of x. So this is the same thing as the integral from a to b. What? Wait, hold up. And when you look at it like that, it doesn't make any sense. But check this out.
Oh,
Here's A, here's B, here's C.
Oh.
Ah. Now, it happens to work no matter where C is, or where A and B are. Ah.
Wait, but then you.
I know! I know. But look at that, right? So here's, this right here is the integral from A to C. Yeah? This right here is the integral from C to B.
yeah.
And so when you add them together, that's the same thing as integrating from A to B.
Yeah.
Yeah, and it looks weird like that, and especially since the C is in the middle. Bleh. But it happens to work no matter how you flip these guys around, which, don't ask.
Wait,
We're
so
not-
like the integral of A to
Well, what I mean is that as long as you have...
So C could be outside.
C could be down here.
Oh, that's right.
Yeah.
And it's still true that the integral from A to C, and
What
this
if
is
we're out in front?
yeah. So here, this is the next thing. How could that possibly be the case? Well, because of this fact, that the integral from A to B of f of x dx is equal to negative the integral from b to a of f of x dx. Yeah, so in other words, if you flip the order of integration, so you're integrating from A to B, it does have direction. If you integrate from A to B, you get one thing. If you integrate from B to A, you get the negative of that.
How is the area?
How could that be, right? How could you possibly, well, because of the definition. Let's look at the definition here. Let's take this side. Let's take this side right here. This thing is the limit of a sum of my f's times delta x. What's delta x?
A minus or B minus A.
B minus a over n. So now let's factor out a negative.
Yeah, so
negative.
oh, it'll be
A
A.
F
plus
times
B.
negative 1 a minus b over n. That's just a negative, right?
Yeah.
Factor out a negative 1. Well, that's a negative limit of the sum f a minus b over n.
Yeah.
That is delta x for this guy, right? Delta x for this one is that one minus that one, a minus b over n. And therefore, that right there
Should be the negative
is
area.
negative limit b a f dx. It just comes from the fact that that's how we define this guy.
Yeah.
Okay? So yeah, if you're going from 0 to 2 of some function, that's the same thing you'd get if you took the negative from 2 to 0. Yeah. And it's just because of this. It's just because of this way we define this. That's all there is to it. And the way that we define these. That's the only thing that's happening. Is it's kind of like when you do your slope and you're like, well, if you always go to the one on the right and minus off the one on the left, it's always positive. But if you go in the opposite direction, it becomes negative. So that's all you're doing here, right? Like it's kind of the same thing, right? So that's it. Oh, well, actually, there's one more thing. So don't let that mess with you. You could just if you really want to pick it apart, it's because of just the definition of delta x, right? And so that's the way it is. Here's a question. You have some function. And you're integrating from some number up to the same number.
Zero.
It's 0. A couple ways of looking at that is like, how much area is there under this dot? There's no area. Another way of looking at it is, this is the limit of a sum of some
And
stuff,
A minus A, yeah.
and
A minus A
then
over
delta x, right? In this case, delta x is defined to be a minus a over n, which is just 0. So everything here is just times 0. So this is the limit of the sum of 0 plus 0 plus 0, which is just still, no matter how many times you do it, still just 0.
Infinity times 0 is 0.
It depends. We haven't done that. We haven't. We're gonna come back and do infinity times 0 because it depends. So that's it, guys. That should be everything you need for the homework. Yeah. Questions?
I don't think so.
No? Okay. Awesome.